Alright, this mini lecture will wrap up our introduction to the Claisen. In fact, it will wrap up our Claisen. It won't be an introduction anymore. After we abruptly stopped our previous mini lecture, this one will have a little bit of an emphasis on synthesis and some examples. So, moving right along, let's talk about synthetic bells and whistles. Now, this is a big overview. This is not just a Claisen. This is to help you prepare for the final. So, when you see, primarily, your target either being the 1,3-keto alcohol or an alpha-beta unsaturated carbonyl, that should be screaming aldol. Alright, so a synthetic bell and whistle, if you see the alpha-beta unsaturated ketone or the 1,3 aldol product, you should be looking at an aldol reaction as a potential way to make this thing. So, for example, this is a complex molecule, but I can see 1, 2, 3 away, there is an alcohol adjacent to my ketone. So I could make this by an aldol reaction. How? I've got to think disconnection. I have to think, where would the enolate be? And of course the enolate would be on the alpha carbon, and this guy would be my former carbonyl. Now what's interesting about this particular example is that what you're seeing is an example of an asymmetric aldol. In other words, the one I'm going to draw up here doesn't have a snowball's chance in the world of giving me an enantiomerically pure aldol product. This asymmetric kind of chemistry is beyond the scope of this class. What I've shown right here will give us a racemic mixture. But nonetheless, we can see that if I generate that enolate and add it to that aldehyde, I will get this product, this target molecule, albeit not in any kind of stereochemical purity. So, there's your first bell and whistle, that of the aldol. Next, we have this bell and whistle, the 1,3 relationship between two carbonyls. That's telling us it's the Claisen. So when we have a molecule like this, say I want to make this is my target molecule, I spy that I have the telltale signs of a Claisen. Again, what I want to think about is, where should my disconnection be? And that means, where should my enolate be? And if I clip off right there, I can see that I could generate an enolate there. This piece could be an ester, and in fact, this would be a perfectly good target for a self-Claisen. In fact, I'll make it a self-Claisen. So 2 molecules of this plus a nice base, we should be able to get this Claisen to go in pretty darn good yield. Should be very favorable. So that's our Claisen bell and whistle. But there's a lot of other bells and whistles that we know. For example, if we see a cyclohexene, I hope we know that that is screaming Diels alder. And if we see an alcohol, we should be thinking alcohol disconnection. Furthermore, this one's a kind of a tricky one. What about a 1, 2, 3, 4, 5? A 1,5 relationship between two carbonyls. What in the world would that be? Well, I'm going to complicate this up just a tad and put an A here and a B here. This is the bell and whistle for a Michael reaction, which means, where would my enolate be? Well, my enolate could be either here, adding to this Michael acceptor, Or my enolate could be here. In other words, I could have enolate adjacent to the other half of the molecule, adding to that Michael acceptor. So, play with your disconnections. I'll give you some practice problems to deal with, but remember, these are all pretty standard hints for synthetic disconnections. Now, before I move on, let's just point out that in this particular alcohol, again, I'm seeing that I have two groups on my tertiary alcohol that are exactly the same. So that is a really good bell and whistle that I should be adding a Grignard or organolithium to an ester, because these will add twice to the ester to give you the tertiary alcohol. Alright, wrapping it up with a specific example of a Claisen. Let's look at this particular reaction sequence. Now, I've got an ester and I've got a Michael acceptor under basic conditions. So as we work through this reaction, as we think about the mechanism and what could happen, we're going to stop at each stage and say, what else can happen? So given that I'm under basic conditions, I can generate an enolate here, or I can generate an enolate here. If I want this reaction to go the way I want it to, I'm probably going to control the addition of the reagents so that I get the enolate I want. So let's say that I generate my enolate on my ester first, and then I add the Michael acceptor to the reaction flask. Alright, in that case, what I'll have happening is, of course, enolates do 1,4. So I will get CH3O, the 1,4 addition, to get this intermediate enolate. So just to make this quite obvious, I hope, here is the ester. Here is where the bond was just made. And here is my Michael acceptor. Alright, is there anything else that can happen? Well, of course there's something else that can happen. We can protonate our enolate, but our enolate's a really good nucleophile, as we know. So, as I look at this, I'm going to look at the resonance contributor and say, well, I've got a great nucleophile and I've got a great electrophile. Can this undergo an intramolecular reaction? And I'm gonna rule that out because it's a 1, 2, 3, 4 membered ring. That is not very favorable. However, as we have seen, enolates can equilibrate. So my methanol can protonate the one enolate, and my methoxide can deprotonate on the other side, so that I now have a very favorable intramolecular reaction. So that's just equilibration, moving our enolate around. Now I have 1, 2, 3, 4, 5, 6. Is there anything else that can happen? Well, you better believe it. Up, down, and out, and my intramolecular Claisen takes place to give me this product. So you should probably work out that mechanism on your own just to convince yourself that yes, indeed, that is the final product. But remember, stepwise mechanism is the key. Show all intermediates so that you can see what might happen next. You ultimately want to get down to a nice, stable final product. Well, this has been a lot, so I definitely think it's time for a joke or two. These jokes, I hope, will be appreciated by all the music lovers in class. This is, of course, a picture of our friend Mozart, who couldn't find his teacher. Why couldn't he find his teacher? Because he was hiding. Get it? And why did Beethoven kill his chicken? Well, it's obvious. Because it kept saying, "Bok, bok, bok." These are really bad. So, I hope this has been helpful. We will do some more examples in class and practice, and review, and we will see you in class.